So I hope like my voice is clear and the screen is visible to everyone. So I've started the recording, and this course is on antennas and radiating systems. So I'll try to briefly introduce this course and the class logistics, and then we'll start with the material. So this slide has I've already introduced myself. Um, So I'll just like it's formality. I'll speak for myself as well. So I'm Anand Kumar, and this is how I look. I'm a Prime Minister's Research Fellow at the Department of Electrical Communication Engineering at the Indian Institute of Science. I'm also a visiting student and researcher at the Tyndall National Institute, which is hosted by the University College Cork in Ireland. I did my bachelor's in Electronics and Communication Engineering with honors at the Indian Institute of Technology, ISM Dhanbad. I got some awards, and yeah, so my research area is specifically space-time varying metamaterials, computational electromagnetics, and non-reciprocal systems. It's heavy words, like they are like very when you do a PhD, it becomes very narrow area. So metamaterials is another course which I usually take. Computational EM is my expertise. So I host different courses. My courses are on YouTube as well. So I'll share the links and everything so that if you find interest, time, try to look at them. Maybe you find interest in them. A lot of opportunities there as well. And non-reciprocal systems is something which I'm uh, doing research right now. So the antennas course that we are doing, they are reciprocal systems, and there is a principle of reciprocity which we'll look into. So it's something related to this. We'll talk about in this course as well. Yeah. So I guess Microsoft Teams is somewhat new, or you might have already used this interface. So I try to keep a slide on this. So there is this chat button over here, which where you can like uh, click, and then the chat window opens. You can post your questions there, just in case like if your mic is not working, or if you have questions in between while I'm speaking, you can post your questions there. There is a raise a hand button over here where you can raise your hand, and if you want to speak, I'll when I pause, I can ask you to unmute yourself, and then you can ask your questions directly as well. Uh, yeah, so these two are the important buttons over here. And yeah, so over here there is a mic button, which when I ask you to unmute, you can unmute yourself and then speak. Otherwise, we'll try to keep only the speaker is unmuted so that there is less interference. And there is this camera button which we can turn on and off based on for the interaction. So when you raise your hand, this is how you can see that the hand is raised, and I will identify who wants to speak first. I guess Microsoft Teams is okay as an interface. Yeah. So why this course? Yeah, I try to keep this slide as well, just to make sure everybody who is attending this course have an insight into why this course would be useful to them. Uh, I'm guessing we have students from BTech and Tech and PhD might be here. So for the BTech students or bachelor BS students, this course could be part of their coursework. I got a syllabus from professor over there that this is part of your curriculum. This course is also important with perspective to GATE exams and other exams. If you want to appear for civil services. This course is part of the curriculum of electrical engineering and electronics and communication engineering. And if you are looking into developing interest in antennas and radiating systems, and when I say antennas and radiating systems, as a joke, anything can radiate if you excite it at the correct frequency. So yeah, so that hence the name of the course, antennas and radiating systems. For MTech students, again, this could be part of your coursework, or your this is part of your interest, or you are doing a specialization in RF. So antennas are very important. For PhDs and postdocs, if you want to just revise the basics because you have already studied this course quite a few times, if you are doing a PhD in antenna. For if you're from industry, then you could use this course as revision of the subject. If you are interested in antennas, if you're from a different area, and if you're applying for higher studies, if you plan, then you might look into this course as well. Your expectations from this course, this is what I will try to deliver. understanding of the basics of the antenna theory and its applications, which is very important. If you are studying a subject, you will expect where will I use this. So I'll try to emphasize on those aspects as well. uh, get a better preparation maybe for gate, or if you're already preparing just as a revision. And through this course, I'll try to incite an interest in you into reading literature on antenna theory, because the textbooks, they're really boring if you have interest in the subject. But if you have an interest, you'll really enjoy going through the textbook as well, and maybe read some research papers in the literature as well on the topics which you are really interested into. This is the course outline. I guess all of you have this already with you. So we'll start with the introduction and basic electromagnetic theory today, and then we'll move on to more antenna-related topics such as dipoles, the antenna patterns, linear antennas, their arrays, receiving, transmit, receive systems, phase transmission formula, which is very important, and then some other types of antennas we'll also try to discuss. For this course, I will be referring to this particular book, which is Field Wave and Electromagnetics by D.K. Cheng. I'll share the textbook PDF with you at the end of this class. Uh, but this particular book, Antenna Theory, Analysis and Design by Konstantin Balanis, this is like the Bible of this research area. But this book is specifically for antenna theory. It's a huge book. So I'll personally prefer to go through DK Cheng, which has a just a chapter which is concise, and like you can go through this at like in a faster pace. And then there are other textbooks as well. Try to read as many as you can if you want to do have a very strong grasp on antenna theory. But just going through, I guess, Balanis is all right. Uh, for the sharing of the materials of this course, like the meeting links, the class materials such as the slides or assignments, the class recordings, we'll do it via the class WhatsApp group. I'm hoping everybody is there. If you are not, please try to join the group. At the end of every lecture, I'll try to send you the slides, and as soon as I have the recordings available with me, I'll share that as well. We can do an arrangement whether you want it on YouTube or just the videos with you. That's all okay. Queries and assignments, like if you have any question, you can just post that in the group and I'll try to come back to you as soon as I can. And I'll request to please regularly check the group for updates regarding class timings. Yeah, and we'll have some assignments, which will be a take-home assignment, which is a quite popular concept in IISc. Professors give us different kinds of assignments. A lot of them are take-home, which means you can just take the assignment. You don't have to solve it in the class or return them. Yeah, you can. The solutions can be shared with you if you want. We can discuss the doubts, but you don't have to like solve the assignment, submit it to me, and it won't be evaluated. The assignments are for you to practice, and I'll be choosing questions from different books and giving it as in a PDF. You can go through more textbooks, solve more examples. I'll just picking some good examples from the textbooks for you to evaluate, like to practice. So hence the self-evaluation is encouraged so that you develop a habit to solve the questions by yourselves. Check how much have you understood this course. And if for all the doubts, you can come back to me in the class, or I'll prefer if you ask the questions in the WhatsApp group so that we can all try to solve a problem. For example, if you have a question and you're not able to solve it, somebody else in the group might have solved it. And then if they teach you, if they share their views on how they approach, it might be better because uh, in the class, if people solve the problems together, it's a better learning environment. So I'll pause over here. I discussed the class logistics. If there are any queries about the class logistics, we can discuss them now. Or if you have any queries in general, after this slide, we'll start with the teaching material. So I'll pause over here, take questions. Please feel free if you have any questions, and professors as well. If you have any suggestions on what I said, please.
I think it is okay. You can carry on.
Okay, sir. Thank you. I'll quickly join from a different device as well so that I can see questions because I'm sharing the screen. Uh, so we'll start with the very basic on and the history of electromagnetic theory. And it's does in high school when we used to have textbooks, we used to have the pictures of the scientists and people which brought the theory or the concepts. But later in the textbooks, now we don't find them. So I try to include the pictures of the scientists who gave us the theories, especially for this particular course, James Clerk Maxwell and Oliver Heaviside. They are like the founding fathers of this area. So, foundations of modern electromagnetic theory, they were formulated in long back 1873 by James Clerk Maxwell, and he hypothesized the mathematical considerations for electromagnetic wave propagation. So he gave like 20 equations for electromagnetic theory, which like encapsulated everything which the research was done before that. And once he gave the 20 equations, uh, the four Maxwell's equations that we see right now were formulated by Oliver Heaviside. So before this, your syllabus would have been very long if Oliver Heaviside wasn't there. You would have been studying 20 Maxwell's equations. But then Heaviside, he introduced vector notations into the Maxwell's equations, and then he condensed them into just four of them. So that's what this course will initially move about, which is the Maxwell's equations. And here are the two handsome personalities who found this electromagnetic domain. So next, once Maxwell had hypothesized the Maxwell's equations, it needed to be tested, and Heinrich Hertz, who was a German professor of physics and a gifted experimentalist, he performed the experiments. He designed an experiment to verify his Maxwell's theory, and in his experiment, this is the picture of the setup. And over here, if you see, there are these two. Metallic balls which are connected by a wire, and this was the the first dipole antenna, and this is where it all started, this antenna theory. So this is the setup of the experiment, and there was the first antenna designed, and this is how they verified the Maxwell's equations. And here is Heinrich Hertz. Yeah. And so next, the important people were Lord Kelvin, Sir Lord Kelvin's real name was William Thomson, and Sir George Gabriel and John Carl Frederick Gauss. Uh, so these personalities gave us basically the divergence or Gauss's theorem and the Stokes theorem, which you might have encountered in your course on electromagnetic theory. And these are the personalities who introduce these courses. So I'm guessing like you have gone through electromagnetic theory before this course, which is a prerequisite for antenna theory, because a lot of things will be based on the Maxwell's equations and the electric fields, magnetic fields, the electromagnetic fields. So these equations are very commonly used while moving from one domain to the other. Uh, so yeah, so divergence and Stokes theorem were given by these personalities. And electromagnetic theory, it can be regarded as the study of fields produced by electric charges in rest, so or in motion. So if there is a charge in space, let me try to use a pen maybe. Yeah. So for example, if there is this charge and it has maybe positive or negative on it, if there is a charge existing in space, it will have an electric field. sorry, electric field is moving outside. You will have an electric field. So if a charge exists, you will have electric field. If this charge is constantly moving in one direction, so then it will start having magnetic fields around it. So for example, if there is a let's say there is this wire which has uh, current flowing in it, and current is basically electrons flowing in a direction. So if there is a current flowing, it will have a magnetic field around it. And now, if this particular charge, if it's flowing with uniform velocity, we have magnetic field. If it's static, we have electric field. And if this charge is now accelerated, so if it starts moving with an acceleration, we will have time varying electric and magnetic field, which launches the electromagnetic wave. So if there is an oscillating charge, we will have electromagnetic wave, and on the basis of the oscillation frequency that determines the frequency of the electromagnetic wave. So here is we have summarized this. Electrostatic fields are usually produced by static charges, whereas magnetostatic fields are produced by electric charges moving with uniform velocity. Uniform velocity is very important in this case. And if this velocity is not uniform, that is, we have accelerated or time varying accelerated charges or time varying currents, we will have uh, we will have the electromagnetic waves. Okay. So let's start with the electrostatic fields. We'll look at the electrostatic fields, magnetostatic fields, and then we'll pause and take questions if there are any. So this is the Gauss law. I'm hoping this you have seen this before. So the Gauss law states, let me change it back to 0 pointer. So the Gauss law states that a closed surface integral of the electric flux density d uh, is equals to the volume integral of the volume charge density uh, of that object. So maybe I can try drawing something on this. Uh, yeah. For example, uh, if there is this closed volume, and if this volume has some charge inside it, and there are electric field flowing outside from this volume, so if you integrate there is this charge inside, and then this charge has electric fields flowing outside, and if you encapsulate the charge in a surface inside with a surface, so the amount of flux which is incident on the surface, if you integrate that, which it will be equal to the total charge which is inside the surface. So this is the charge density which is inside, and if you take the volume integral of this area, this volume with the charge, you have your right hand side, and if you integrate the flux density on the surface of this volume, you will have your left hand side. So Gauss's law states that. And in the differential form, we can write it as in the differential form. This is given as the divergence of the electric flux density. So I'll quickly write this. So if you take this delta of a vector uh, field as a scalar product, this is divergence. I'm sorry, I don't have my stylus with me, so I'll have a bad handwriting. Divergence. So just for like remind, this is divergence. If you take the delta and cross product of the vector, it becomes curl. It is called curl. And if you have a scalar quantity and it is just a multiplication, this is gradient. Okay. Sorry for the terrible handwriting, but uh, so when I say the notations, this is divergence where we have this scalar product. If this is a vector product, this is curl, and if we don't have a vector over here, this is a scalar quantity, then it's called uh, gradient. Okay, back to the electrostatic fields. So this is the Gauss law in its integral and differential form, and the law describing electrostatic fields are conservative. That is closed loop integral of electric fields on a line, uh, it's equals to 0. That is, if you move around a circular line, the total electric field will be 0. Maybe will need to, I can draw something like this. So electric fields, they are parallel in lines. The electric fields, they never meet. So the electric field, so for example, if you have a space where you have electric fields, and if you try moving in a circle in the electric field, and if you integrate, you'll end up with the value will be 0 because electric fields, they are not in circles. So that's what this says, and this has deeper physical significance as well. And its differential form is the curl of electric field, it's 0. Next, the electric flux density and the electric field intensity, they are related by this constitutive relation. D is equals to epsilon E, where epsilon is the dielectric permittivity of the media. So dielectric permittivity is one of the constituent parameters which defines the media. So the other constant would be dielectric permeability, and your conductivity of the media, and they basically define a substance. Is there a question?
नकऱ्याकडे पहिला माल याला ही गाडी आवडते बघ लाल ड्रेसचा
Okay,
त्याच्या पलीकडे
I'm guessing there is some noise.
आपल्याला
Maybe I'll. Okay, so I'm guessing there was some noise. Let's go back to the slides. Okay, so we were discussing electrostatic fields. We have seen the Gauss law, the differential form, uh, and the law describing the electrostatic fields, that they're conservative, and its differential form, and the relation between the electric flux density and electric field intensity. Next, in terms of electric potential V, so this is very important. So this is very important for us. Uh, this electric potential we will come across a lot in this course when we are discussing antenna theory, because we'll use a way to solve the electric fields in the antennas without having to integrate too much. Integration with these complex equations is really difficult, so we'll try avoiding that. And for that, we introduce this electric potential B, which is also the potential that we talk about when we are solving a circuit theory. So potential and currents is all we look at the nodes and in the branches. So this is the electric potential, and it's given as the divergence of V. The electric field is given as the divergence of the electric potential. It can also be written in this form, where we have the electric potential V is the integral of electric field. And if we combine the equations that we saw just now, the divergence of electric flux, uh, the uh, the electric flux relation with the electric field, and the electric field relation with the electric potential. So if we combine them, we get the popular Poisson's equations, which is very which might be asked during exams, and the questions might come around this. So the Poisson's equations is the divergence of uh, epsilon times the the gradient of electric potential, which is equals to the charge volume charge density. And if usually this epsilon is constant, so this simplifies to del square V equals negative times rho V by epsilon. So this is the popular Poisson's equations, and in under the case when this if your volume does not have any charges, this becomes the Laplace's equation. So, and these are the name of the equations, and there might be questions around it. So you have to remember the name of the equations if you see this. If they might tell you that in the questions that use the Laplace equations to solve something like this, so you will have to remember this particular equation where del square V equals to 0. And when they say that you are using the Laplace's equation, it also means that there are no sources, there is no charge inside the volume. So that's what this implies, that the rho V is 0. Okay, so maybe before we start the magnetostatic fields, I'll just pause over here. Um, Maybe if you have any questions, or I could pause at slides if you want to read them. I don't see any hands, but anyways, I'll wait for some time because we have been going through slides and it might get heavy. I'm guessing I'm teaching very well because there are no questions, which is good for me. Uh, but if you have any questions related to anything, like for example, if you don't follow the equations at all or the things that we are talking about, you can ask the questions like, where can we study this? I want to revise this topic, which is the best material? Things like that are also good. Like they are also very important questions. Anyways, what I can do is I could share the textbook and tell you the chapters where you can see these equations, and maybe good courses on which are free on YouTube, which you can refer to this. So we were looking at the history of up till now. We were looking at the history of electromagnetic theory. We talked about some important personalities who gave birth to this area. Then we looked at how we get the electrostatic fields and the magnetostatic fields and the electromagnetic fields due to the motion of charges. Then we started with electrostatic fields, where we looked at some of the equations and we'll discuss what is curl, divergence, gradient. We have now just derived Poisson's equations and the Laplace's equations. So this is all we have until now. Next, we move to magnetostatic fields. So the notations over here are the magnetic field intensity is H, the current density is JE, and the magnetic flux density is B. So I'll try to keep the vectors in bold so that there is distinction. Might not be consistent throughout, but I'll try to do that. And the Ampere's law is the closed loop integral of magnetic field is equals to the surface integral of the electric current density. So let me try to draw a diagram to the best of my capability. So for example, if you have this wire which is carrying current I, okay, so we have a current carrying wire, and this has some cross section. Okay, this wire has some cross section. So we can calculate the current density, which is J is equals to current by the cross section area. So let's say the area is A, not let's not use A. Let's write the formula. This is, I guess, 2 pi r square is the surface area of, oh no, it's pi r square. Yeah. So pi r square. Sorry, I'm not really good at maths, although I'm good at electromagnetics theory. But yeah, so the current density you can calculate from the area and the cross section of the wire. And now you have the current density, and what you can do is integrate the current density over this surface, and you can get this becomes the quantity equal to on your left hand side, which is, for example, you have the magnetic field. So this current carrying wire will have magnetic field around it, right? It will be like this. uh, you will have current, you have magnetic field like this. So if you integrate the magnetic field across this line integral, if you move along this line and you integrate the magnetic field, you'll get the this quantity over here, and which is basically equal to the current. Current inside the wire. Okay, and now the differential form of this equation can be given as the curl of magnetic field, which becomes equal to the electric current density. Next, the law of conservation of magnetic flux. This is also called the Gauss's law for magnetostatics. States that the closed loop integral of the magnetic flux density over a surface is zero. So it basically says if you have since your magnetic field lines are in closed loops, if you integrate over a surface, it will end up zero, because the magnetic lines are in closed loops. So and you can also say this in differential form as the divergence of magnetic flux density is equals to zero. This also comes from the fact that this also means that there are no magnetic monopoles. So there are no magnetic monopoles, and this fact comes from this equation. Next, so we have the vector fields, magnetic flux density and magnetic field intensity, and they are related by this constitutive relation, which is B is equals to mu H, very frequently used during substitutions. And this mu quantity is the permeability of the medium. So earlier I said we have epsilon, now we have mu. So these two quantities basically define the properties of the media. So any media that exists, any material, they can be specified by their epsilon and mu. And the current density is related to the electric field through conductivity. And this is the another constitutive relation, that the current density is equals to sigma times the electric field, and sigma is another uh, quantity which specifies the media. Usually, the epsilon can encapsulate the sigma as well, but when we are specifying the media property, we can also write epsilon, mu, and sigma, and this basically will completely specify the media. Sigma can also be represented with the uh, so sigma at times can be represented as A plus JB form, and that is the complex quantity. And when we write epsilon as complex quantity, sigma is usually included in the imaginary part. So essentially, if you have the complex notations of epsilon and mu, you can completely specify a media. And this is usually referred to as the point form of Ohm's law. Another very popular question during theory exams, I guess, they would ask you to derive the point form of Ohm's law, and this is what you have to reach to. The magnetic vector potential, again, so we discussed about this the for the antenna theory course A, which is the magnetic vector potential. and V, which is the scalar electric potential. A is the magnetic vector potential and V is the scalar electric potential. And these are two important quantities that we are introducing to help us solve the equations in future. So it will come up towards the end of this class. And this is by applying this identity. So this identity is basically a mathematician's job. So math people have given this to us. So we don't have to worry. We'll just use it. So the vector identity says that if you take the curl of the same vector, you get the gradient of divergence of the same vector minus the del square gradient square of the same vector. Okay, so by using this identity, what we'll do is and there is this assumption given to us by scientists, so we won't worry about this. Something is called as the Coulomb's gauge equation condition. This is the divergence of A is zero. So this is known to us. Okay, so we won't worry. We will just take this. Somebody has told us, and this is true. And this leads to the Poisson's equations for magnetostatic fields. So what we have done is uh, we had this quantity del divergence of A, and we what we did was we took sorry, curl of A, and once we took the curl of A, we got this divergence of sorry gradient of divergence of A minus the L square of A. Now we just said that Coulomb's gauge equations tells us that the divergence of A is zero. So this quantity over here, this becomes zero. And so we are only left with del square of A, and del square of A is equals to mu JE. And we get mu JE from substitution over here. Uh, yeah, so we have B over here, and this B can be written as mu times H. Okay. Something fishy over here. Okay, we'll come back to this. Anyways, so this is the Poisson's equation over here. So this is the Poisson's equation for magnetostatic fields, and the similarly we had the Poisson's equations for electric field with L square V is equals to rho by epsilon. So if you can see, they look pretty much similar. So most equations in electromagnetic theory, they are duals of each other. So if you remember one of them, it's very easy to substitute one for the other. And when your source, that is the current density, becomes zero, it becomes the Laplace's equation. Similar to the previous case where if you had a source, if you don't have a source, the rho became zero, and we had del square V is equals to zero. Similarly, if you have uh, the current density equal to zero, this becomes the Laplace equation for magnetostatic fields. So this is all for the magnetostatic fields. We have covered electrostatic fields, magnetostatic fields, and next we'll see time varying fields. Maybe we'll just look at the Maxwell's equations and end the class for today because it's been already very long. And we'll try to catch up over the next classes. So this is James Clerk Maxwell again, and he gave the Maxwell's equations. So earlier I was talking about the Maxwell's equations. So from the previous discussions and further discussions, we have the Maxwell's equations with us, which is basically the divergence of the electric flux density, divergence of magnetic flux density, curl of field intensity, and curl of magnetic field intensity, and they they give us these four equations. And it's also said that if you have a vector, for example, let's say if you have a vector r, and if you know its divergence and if you know its curl, it is said that you have the complete information. So if you have the knowledge of the curl and divergence of a vector, you have the complete information. So we know that this d is related to is said as epsilon e, right? We have this as epsilon e, and similarly b is mu h. So essentially, we have the divergence of E and curl of E and divergence of H and curl of H, which basically defines the entirety of electric field and magnetic field that we need to know to solve problems. So in this slide, we have the notations written with us and with along with their units. Might be important while solving problems so that you don't mistake them, because usually for realistic problems, these are very small and large quantities and senses. So electric field is usually much larger in value as compared to the magnetic field from the relations. So make sure you have the units correct with you. And the Maxwell's equations are again has different forms. So I'll tell some things about this as well. So we have the Maxwell's equations in the differential form over here, which we just saw. They can also be written in the integral form, and over here, from moving from here to here is in different directions. We use the Stokes equation and the Gauss's Stokes theorem and the Gauss's theorem is where we move from the differential form to the integral form. And they can also be written in time domain. Over here we have, you see, we have d by dt terms over here. Again, we have d by dt terms over here. But they can also we can also replace this d by dt for harmonic expressions with j omega. And when we replace these equations with j omega, now we are representing them. This omega is nothing but 2 pi f. And once you replace all the d by dt terms with j omega, you will have the frequency domain forms. So Maxwell's equations, you can divide it into four quadrants, and you can have time domain representation. Let's say on the top we have the time domain representation, and the bottom we have frequency domain representation. And then you can also divide them in form of integral or differential form. So you can also have integral form over here. Okay, this is very tough to write. Uh, Integral form, and you can have your differential form, differential equations. So in this case, you will have time domain integral equations, frequency domain integral equations, time domain differential equations, and frequency domain differential equations. So over here, I can introduce my research area. So what I do is time domain differential equations. It's also called finite difference time domain equations. And here is my research area as well. for computational methods. More on this we can have it towards the end of this course. We can discuss what I do and how I got into IISc and things. Yeah, so this is so Maxwell's equations, it can be written in four forms. Two of them are here, differential form and integral form in the time domain, and you can write the frequency domain by yourself by just replacing d by dt with j omega. And these equations, they become complete with the constitutive relations, which relate the electric flux density with electric field, magnetic flux density with magnetic field, the current density with the electric field, the magnetic current density with the magnetic field. Yeah, magnetic field. I guess there's some typo over here. Okay. So this expression is basically fictitious. It is basically the dual of this expression, and these two are the dual of each other. Okay, so maybe we can stop over here because I have few more slides on antenna theory introduction, but they will take time, and I guess this class has extended for almost an hour, and I guess I believe that we probably stop learning at some time because we get saturated. So I had a few slides, but maybe I'll introduce them in the next class. Um, and these slides were basically on introduction to antenna theory, and why antennas are important, what we will look at. And there were some heavy equations coming up, but we should stop. Um, I'll stop here. Take questions if you have any questions on the material, class logistics, about me, or if you just want to talk about you, that's also good. Okay, I don't see any hands. I guess everything was like the best teaching I've ever done. Like, I have no doubts. Okay, just a question. I was audible, right?
Yes, sir. Your sound is very
Yes.
much clear. No issues
Okay.
on it.
I'm guessing the students are a bit intimidated. Is it like because I was guessing there would be more questions on me on why am I teaching and why do they need to do this course? But
They will open up after two, 3 lectures. No issues.
is it because their professor is here and they are like they might get a scolding from you?
No, it is not like that one. They
Okay, I
will
was just
ask.
joking.
Yeah.
Okay. So
Yes.
thank you guys for joining. And if there are any questions, if you can also message me personally in the WhatsApp. You have my number there. I'll I'll post the slides now. So if you have any questions that you want to ask me directly, that's also good. And I can speak Hindi. So if you have questions, like I don't know Marathi, but I can speak Hindi. Sort of okay. So you can ask questions in Hindi. Chalega मेरे को. Okay, so I'll stop sharing now and stop the recording as well. I'll share the recording as well with you.
So thank you, Mr. Anand Kumar. Tomorrow
Okay,
we'll
thank you
start
so much, boss.
at the same time. I request all
Uh,
the students to join at right
so
time.
I had a suggestion. I have a meeting tomorrow with my professor in India. Can we do this class on Thursday? Is it okay?
No issues. We
Because
can
he's
start.
it's again the same issue because the time difference. It's the only duration when I can arrange the meetings with him. So tomorrow I have a meeting, but Thursday is good. We can do a class on Thursday
Okay,
and we
no
can.
issues. We can start on Thursday at 6
Okay.
p.m.
Okay.
And please share the slides.
Yes, sir. I'll definitely do that right now. Um.
Okay.
Okay.